somewhere in the middle, right? So not from the beginning to the end, but somewhere in the middle, so that neither of the interfaces are exactly at the boundary. Why that is because I want to find Tm as a function of x for the whole tube, right? So we cannot do macroscopic energy balance for the whole liquid in the whole tube, right? So because then we will not get Tm as a function of x, right? We need to make sure that it's a shell of some small distance thickness delta x, which then we will assume to approach 0, or let me even say it's directed dx. But in principle, you can also write delta x and let's say delta x approaches 0, right? It's same. Okay, so if we do this thing, then we need to write energy balance. So what terms we need to include? What do you think? In the energy balance, so what terms will contribute?
So QS.
QS double prime, right? But we need to write it in terms of energy flow rate. So what do we need to multiply it with?
Volume.
Area, right? So but which area? Okay. 2 pi r naught L delta x or dx, right? If we call dx, then dx. It's equal to what? So this is energy which leaves this volume element through the external surface area, right? And what it's compensated with? Okay. I'm writing it in terms of m dot, right? Cp dTm. Remember that we are using here mean temperature because Tmi is given, so we want to use expression in terms of the mean temperature, not in terms of T, right? Which will be also a function of R, but in terms of dTm. And this is the same type of expression as we used before, except that Qs is now not constant. But we can deal with it because it's just mathematics. So we substitute our expression which we know, and simply write that it's Ax 2 pi r naught dx is equal to m dot Cp dTm. And then we can separate variables and solve. So we can say that dTm is equal to 2 pi r naught Ax dx over m dot Cp, and integration of both parts. Well, we either can just take integrals without defining limits, or we can integrate within limits. So one of the limits should be variable, because we want to have a variable inside, since we need Tm as a function of x, right? So only if one of the variables is one of the limits is variable, right? Then you will get Tm as a function of x. And usually we define upper variable, upper limit as variable. So it's Tm corresponding to x. So what will be the lower limit?
Tm.
Okay. And here?
0.
0. Okay, so this is just a boundary condition, right? So we use boundary condition for the lower limit of integration. So we integrate and get expression for Tm as a function of x. That is Tmi plus pi r naught a over m dot Cp x squared. So now we see that it's the x squared dependence of Tm, right? So which is stronger than what we have seen before for Qs equal to x. So you can see that we can solve this problem without making assumption about whether it's thermally fully developed or not, right? So we don't need it. We don't need this information at all to solve this particular problem, right? Okay, guys, so any questions, concerns, or something you would do differently here? Okay, so if everything is clear, then Pudi have your second homework, already third homework graded, right? And also he wanted to get to regrade second homework, right? Did you want to regrade second homework? Did you want to regrade second homework?
Yeah, sure.
So
They asked them to bring back the second one, so they can.
so you can bring back your second homework for regrading if you want to.
Hey, what happened to that sheet? Is that sheet still floating around? Or is it still
Yeah.